Okay, Monica ma'am, should we start?
Monica ma'am?
Yes, we can start.
We can start. Nina ma'am, go ahead. I think we should start. Let's see.
Okay, ma'am.
Let's see. Hello?
Yes,
ਹੁਣ
ma'am.
ਤੂੰ ਵੈਬਿਨਾਰ ਲਾਉਣਾ ਮੇਰਾ ਟਾਈਮ ਹੈ 3 ਵਜੇ ਦਾ
Hello?
Ma'am, shall I start?
Let's see if the speaker is there. We'll tell him also. No, we are starting. We'll ask the speaker that we're going to start. So then we start. Let's see if he's there.
I'm still here. Yeah.
You're here. Dr. Antoine, you're here?
Sorry?
Okay, now Dr. Antoine, we are going to start the session. We'll be introducing you and then we start. Okay, Nina, go ahead.
Yes, madam, we are ready. You start, ma'am, please.
Okay, ma'am. A marvelous afternoon to all. To raise new questions, new possibilities, to regard old problems from a new angle requires creative imagination and mark real advance in science. With these lines, I, Dr. Neena Sharma, welcome you all to the second talk of International Webinar Series on Compact Radiation Sources and Applications in Sciences, jointly organized by the Department of Applied Sciences and Humanities, RKGIT, and RKGIT Pharmacy. Laser, a device that stimulates atoms or molecules to emit light at particular wavelengths and amplifies that light, typically producing a very narrow beam of radiation. The emission generally covers an extremely limited range of visible infrared or ultraviolet wavelengths. Laser is an acronym for light amplification by the stimulated emission of radiation. Radiotherapy is playing an ever-increasing role in the treatment of cancer and other illnesses. Compared to other treatment options, it shows a good response. Regarding this, today we have a very interesting topic, laser-driven sources in radiotherapy. Our speaker of the day is Dr. Antoine Maitrallain, Research Fellow, Department of Physics, University of Strathclyde, Glasgow, Scotland, UK. We welcome you, sir. Now, I request Dr. Monica Sachdeva, Principal RKGIT Pharmacy and convener of the webinar series to deliver welcome address. I over to you, ma'am.
Yeah, thank you, Dr. Neena. Our speaker of the day, Dr. Antoine Maitrallain, Research Fellow, Department of Physics, University of Strathclyde, Glasgow, Scotland, UK. Dr. Poonam C. Kumar, Head Applied Sciences, convener of this webinar series. Dr. Sanjeev Goel, Professor, Department of Applied Sciences, and Mr. Abhinav Agarwal, Dean Academics, RKGIT Pharmacy, coordinators of this series. Mr. Vikas Katoch, Assistant Professor, Department of Applied Science, and Mr. Pankaj Sharma, Assistant Professor, RKGIT Pharmacy, co-coordinators, Mr. Santosh, Assistant Professor, Department of Applied Science, heads, coordinators, faculties of different departments, and all the distinguished participants. A very good afternoon to all. We know that though the rate of survival is increasing year by year, but the cancer, it still remains one of the major cause of mortality. We are seeing new cases of cancer rising each day. And as per the literature I was going through, about 50% of the cases, they are treated with radiation therapy in combination with surgery and chemotherapy. In comparison to other treatment, main goal of radiation therapy is to achieve local tumor control, selectively kill cancer cells without causing any significant damage to the surrounding normal tissues. And this radiation therapy, it uses high energy ionizing radiation, and lots of advancements they have been made in radiation therapy using different types of rays. Which may ultimately affect the outcome of the therapy. Dr. Antoine today will apprise us all about various laser-driven sources of radiotherapy. And it's our privilege today that participants from all different fields, disciplines, they are connected with us today on this platform. So with all these words, I, Dr. Monica Sachdeva, on behalf of all of us at RKGIT, wholeheartedly welcome Dr. Antoine, all the dignitaries and all dear participants to this second day of the webinar series on compact radiation sources and applications in science. So thank you. With these words, I will
Thank
over
you,
to you,
ma'am.
Dr. Neena.
Thank you, ma'am. Now, I would like to request Dr. Sanjeev Goel, Professor Applied Sciences and Humanities and Coordinator of Webinar Series, to introduce the speaker of the day. I over to you, sir. Sir, please unmute yourself.
Thank you, Dr. Neena ji. Am I audible?
Yes, sir.
Okay. Let me read out the brief profile of Dr. Antoine. Dr. Antoine is working as a research fellow at the Department of Physics, University of Strathclyde, Glasgow, Scotland. Dr. Antoine Maitrallain did master degree with honors and PhD from the University of Paris, Sclay in 2017. Since November 2017, he has been research fellow at the University of Strathclyde in the group of Professor Dino Jaros-Niski, working on the laser wave field acceleration and the related applications. His research covers a range of topics in intense laser matter interactions, including laser-driven electron acceleration, associated secondary sources, and the design of magnetic elements to transport and diagnose high-energy electrons, etc. Currently, he is working on laser-based compact radiation therapy. He has supervised master project in the field of laser wave field acceleration and guiding a number of PhD students. He has published more than 25 research papers in highly reputed journals. Now, I invite Dr. Antoine for giving the lecture on laser-driven sources in radiation therapy. Welcome, sir.
Thank you very much for the introduction and hello everyone. Let me just start sharing my screen. Can you all see my screen now?
Yes, sir, we can see your screen.
Okay, great. I might stay without the camera on just in case I have network issues. That might be easier. I'll switch it on during the question session. All right. Okay, so thank you very much for the introduction and thank you for giving me the opportunity of presenting this work today. So as has been said, I'm Antoine Maitrallain. I'm a research associate in the Strathclyde Intense Laser Interaction Studies group at the University of Strathclyde in Glasgow, United Kingdom. So I will discuss this main graph that I'm showing here a little bit further during this talk. So I'll not describe it in too much details now. I'm here to talk about laser-driven sources in radiotherapy. So before I even start, I would like to thank all the collaborators who contributed to this work. So a good part of the work I will present now was undertaken at the University of Strathclyde or by our group, partially at least. And some is from external sources as well. But by our group, I mean the group I'm part of at the University of Strathclyde, but also collaborators we have in the biological department of the University of Strathclyde, collaborators at the University of Glasgow, at the Diamond Light Source and Imperial down in England, and at the School of Medicine in Indiana University. To start with, I'll just quickly comment the outline. I'll start with a little bit of context and back on the history of what radiotherapy is. I'll discuss what do I mean by laser-driven sources, and then I'll discuss the applications we're intending to study with these laser-driven sources, namely electrons, X-rays, and protons, and then I'll conclude. So first, a little bit of history on what radiotherapy is. So that's been discussed earlier in the introduction. But basically, the aim of radiotherapy is to kill cancer cells while minimizing the damage on healthy tissue. So basically, what you want to do is deposit those where the tumor is and keep the surrounding healthy tissues well healthy and not damaging them. So it's first started in 1895, shortly after Röntgen discovered.
Excuse me, Dr. Antoine, can I disturb you? Your voice is not very clear. Can you speak a bit louder?
Can I speak a bit louder? Sure.
Yeah.
Is that okay now? Or?
Yeah, it's okay now.
Okay, great. So it first started in 1895, shortly after Röntgen discovered X-rays. So the same year, basically a couple of months after that, several groups started using X-rays in radiotherapy treatment. One of them was a group led by Dr. Emil Grubb, who interestingly died at quite an old age, but after more than 90 different tumors started spreading over his body throughout the years just because of misusing of X-rays at the time. I mean, they discovered X-rays in 1895, and just a few months after that, they started using it for radiotherapy. So you can imagine that it was not as developed as it is today. Now, another source that is used is electrons. So they've been used since the 50s, electrons up to 25 MeV roughly, and as again an external beam therapy. And in 1946, it was initially suggested to use Proton's beam, and the reason for that is they have an interesting behavior that's called the Bragg peak effect, where basically all the protons, will enter the tissues and start delivering some of their energy inside the medium, and then there is some sort of threshold effect where all the protons will release all their energy at the same time inside the tissue, and that's called the Bragg peak. But I will come back to this later. Then the next advance was about in the 70s, where computational tomography came into play. So computational tomography, or CT, is a new way of imaging tissues where you would take, as in tomography, you would take images of the same region at different angles to try to reconstruct a 3D image. And based on this computed tomography, several new delivery techniques have been developed, one of which is the gamma knife, which an example of is shown here, where you have a number of different radioactive sources emitting gamma rays. And then on the patient, there is an additional shielding so that all the gammas that are emitted will hit precisely the target. And this type of technique increases the dose conformation. That is the fact that the dose will only be deposited where the tumor is and not on surrounding healthy tissues. So that's a little bit of history. Now, the context of today is that every year there's about 17 million new cases of cancers, and this number is foreseen to increase to about 27 million in 2040. So there is a need for developing the radiotherapy techniques, the delivery techniques, but also the diagnostics surrounding radiotherapy. And our question here is, can laser-driven sources have a role to play in this research field? Okay, so the three different media that are available are X-rays. So now I'm going to say X-rays, but this will include gamma rays as well. I'm not going to make any distinction there. Then the next one would be electrons, and the third one is protons. Now, if we go back to the initial plot I showed on my first slide, here you see the depth into water, and here on the y-axis you see the relative dose. So now, why do we choose water to emulate human tissue? It's because it's very similar. Basically, it has exactly the same, or almost exactly the same response in terms of dose deposition. So that this is the only reason why we're using water instead of well, on this axis. And what you see here on the graph is a tumor which is basically located between 12.5 and 17.5 centimeters inside the tissue, or in the water, if you want. That's very well, that's equivalent. And the blue curve here is the dose deposition of a 6 MeV X-ray beam. So as you can see, you deposit those basically from the skin up to deep 30 centimeters inside the patient, basically. Now, if you take the green curve here, it's electrons, 200 MeV electron beam. And again, you see that you deposit some dose in the tumor, but again, most of the dose is deposited outside the tumor before and after. Again, this is not what we're looking for. We're looking to spare the healthy tissue. Now, in purple here, you see the proton beam dose deposition. So as I mentioned before, you have a little bit of energy of dose that's deposited initially, but then there's this sort of threshold effect where all the protons will deposit the energy and dose at the same position at the same depth in the tissue. Well, basically where the tumor is in this case. And now, if you use different energies for the proton beam, then you can cover the entire region where the tumor sits, and that's basically, well, very conform as we were looking. And well, this is what's used in proton therapy now, and this is very efficient. Now, by laser-driven sources, I'm pretty sure Professor Jaroszynski discussed this with the ones who were able to attend his talk. But first, I'll discuss what I mean by lasers. So usually we use from a couple of joules to tens or hundreds of joules of laser energy. The pulse duration is from femtoseconds to tens of femtoseconds, and that leads to peak powers of terawatt to tens of petawatt. And then either you choose to focus these lasers into gas targets, leading to most of the time the production of electron beams, or you choose to focus these lasers onto solid targets, leading to the production of proton beams. So I'll briefly come back on the mechanisms there, but that's the main idea. And then using these electrons or these protons, you can then generate secondary sources, X-ray sources, for example, which I will discuss later in the talk. Now, if you look at the acceleration length that are involved in these cases, here with laser wave field acceleration of electrons in gas targets, you're talking about millimeters to a couple of centimeters of acceleration length. For proton acceleration in solid targets, you're talking about, well, the thickness of the target, which can be as low as tens of nanometers. And now, if you compare this with what's done in conventional accelerators, well, the length of these is the typical length is much bigger. It's about a couple of meters. Now, of course, if you take into account the laser footprint and the vacuum chambers and everything that are involved in laser-driven sources, it kind of matches. But if you take very high energy conventional electron sources, such as the SLAC, which is the LINAC in Stanford, you need about 3.2 kilometers to accelerate electrons up to 50 GeV. So I think what I'm trying to say here is that these laser-driven sources, they can be much more compact, at least in terms of acceleration length. They can be cheaper if you compare them with high-energy sources, and they are much more versatile in the sense that if you change the laser parameters or your source parameters such as the density or the thickness for a solid target, then you will change the output source properties. So they are much more versatile than a conventional accelerator that is designed typically for a given energy and charge. And if you try to tweak these parameters, well, it's not as easy as for laser-driven sources, I would say. So now coming back a little bit more into details into these different sources. So starting with the electrons, so I will not come back on the laser wave field acceleration mechanism because I believe Professor Jaroszynski described this before. What I'll just say is that, so basically, again, you focus high intensity laser onto a gas target, and then you have basically two electron populations that are generated. Now, the one in dark blue here is what we call the forward electron bunch. It is a very short bunch with a low emittance, a high energy, a low energy span, and a fairly low charge. Now, the hollow cone that you see in lighter blue is called the side electron beam. It shows an extremely high charge, but a much lower energy. So to sum up, I put together this table where you see that the forward electron beam, well, its energy is of about 100 of MeV to GeV. So the record is 8 GeV at the minute. The energy spread can be as low as 1%. The divergence as low as 1 millirad and up to 10. It's emitted on the laser axis. It has a duration of about 1 to 10 of femtosecond, and the charge is from 1 to 100 of picocoulomb. Now the side electron beam, it has an exponential spectrum that cuts off at about 2 MeV. It's quite divergence of about 10 degrees. It's emitted 45 degrees from the laser axis. The duration depends on the source length, but it can be of about 100 femtoseconds to picoseconds, and the charge is quite an enormous amount of charge of the order of nanocoulomb to hundreds of nanocoulomb. Now, we can use these electron sources to generate secondary radiation through different processes, and I'm just going to discuss two of them, which are Bremsstrahlung and betatron. So Bremsstrahlung, in this case, you use, so you have your electron beam to hit what's called a converter target, which is a high Z material. And in this material, the electrons will slow down because of their interaction with the material and emit X-rays. And this equation here gives the energy loss per unit path length. So what you can see here is that the X-ray properties will depend on the energy of the electrons, but also the thickness and the material that's used as a converter. Now, if you look at experimental data, our group gathered about 8 years ago. So using, well, with an electron beam of about 300 MeV energy, you can reach, well, you can obtain an X-ray spectrum such as this one, extending up to, well, 10 MeV in that case. Now, the other thing you can look at is betatron. So when we think about betatron, so what we mentioned here, well, sorry, I'll start over again. Here, what I'm showing is the result of a PIC simulation, so particle in cell simulation, showing the density map. So here the laser is propagating from left to right. This is what's on the right of the screen here. And in the wake of the laser, you have the plasma wave. Now in the plasma wave, in here you have electrons that are injected and that will be accelerated in the plasma wave. That's the basic of laser wave field acceleration. Now these electrons, while being accelerated, will oscillate in the plasma wave. And these oscillations will lead to the emission of what's called the betatron radiation. Now the spectrum is given by this type of equation here. And basically the radiation will depend on the electron energy, but also the size of the electron beam and the size of the plasma wave. Oh, I don't know what's happened. Right. And we can today reach peak brilliance that is very close to conventional sources. So this type of X-ray source is very interesting, and it's already competitive with conventional sources. Now the third source I want to discuss is protons. So there are several ways to accelerate protons. The one I'm going to describe is called TNSA. That stands for Target Normal Sheath Acceleration, where basically you have a laser pulse that's hitting a solid target. What will happen is that high intensity laser pulse. What will happen is that it will heat a population of hot electrons that will escape through the back surface of the solid target, and thus that will create a space charge force that will potentially accelerate some protons in their wake. So again, a small table to remind all the parameters. So again, the energy of the protons accelerated shows an exponential spectrum from tens of MeVs to 100 MeV, which is the current record. The divergence is of about 10 degrees again. The duration is of the order of hundreds of femtosecond, and the charge, well, it depends on which particles you're accelerating. So I put the number here in terms of number of particles, and then it depends the ionization states of the particle you accelerate. Now I'm going to switch, now that I've discussed the different sources we're interested in, I'm going to switch to the applications we're interested in Strathclyde. And here is a non-exhaustive list. The one I will specifically discuss are underlined. So I'll discuss very high energy electron therapy. I will discuss flash therapy. I will discuss imaging as well, and isotope production. Okay, so I will start with the direct use of electrons. So as I said before, up to 25 MeV electrons are used in direct radiotherapy until now. But now if we look at the dose deposition of these electrons in tissue, you can see that with 25 MeV electrons, you can't reach much deeper than, well, 12 to 15 centimeters. Again, if you increase the energy up to 50, then you can see you increase the depth, reachable depth. But still, you have this issue of a very broad deposition zone, which again is what we're trying to avoid. We are trying to focus the dose only only where the tumor is. The other thing, this is, and again, if you increase from 50 MeV to 200 MeV, you have this green curve right there. So what we're trying to look at is what can we do to make this dose deposition more conformal into the tumor. Now, the other thing we're interested in using directly the electrons is use them in flash therapy. So flash therapy means a very high dose rate. So when you're using a very high dose rate that is higher than tens of grays per second to irradiate tissue. And this is not very well understood yet, but this is something we could study with both our side electron beam that I mentioned, but also the forward high energy electron beam that I discussed earlier. And since this is not very well understood, this is very active at the minute, and this is a very interesting field. So coming back to the very high energy electron therapy. So what I just talked about is that increasing the energy, you increase the depth that you can reach, and the number of tumors that can be treated with these electron beams. So not only you increase the depth, but you also reduce scattering, transverse scattering in air and tissue, meaning you reduce the loss, the dose that is lost. You also need fewer electrons to produce the same dose as with photons. And it is, in the end, very easy to shape with a magnet or with plasma. You can shape electron beams quite easily compared to protons and photons. Now, everything I've showed so far was based on simulations almost. But here on the right, you can see measurements we've done where we placed films at different thickness in a water tank, and we were detecting electrons, and what you can see is the signal of these electrons is decreasing as we go further inside the water tank, deeper inside the water tank. And that is something that is fully reproduced with simulations. So what we're doing is not only based on simulation and theory, but it's also something we've tested experimentally. So still, we have this issue of what can we do? How can we focus more the dose inside a patient? So one of the ideas we had was to use our normal diverging electron source that we usually have and then focus it using a magnet or a plasma, as I just mentioned. Now, if you do this, what happens is that the dose will only be, will mainly be deposited, well, in that case, at 15 centimeters depth in the water. And if you look at it on the graph I used to show before, this is, so we have all the four curves we used to, well, are already presented. But now, if you look at the red curve, this is using 200 MeV electrons, but focused. So that is to be compared with the green curve here. And again, you see that here, the conformation of the dose deposition inside the tumor is very good. This is much better. You don't deposit those on the skin or very deep inside the patient, but only where the tumor is. Now, if you increase even more the energy of the electrons, well, you're outside the so-called very high energy electron regime, but you have an even more conformal dose. The black curve here is a 2 GeV focused electron beam, and then the sort of light red or dark red, should I say, line here is for a spread out dose around 2 GeV. So using a different focusing system, then you can have your focal point at different depths inside the patient. But now VHE, so very high energy electrons, are defined between 50 and 250 MeV. So let's stick with this. But even in this energy range, we can have an effective depth that can exceed 40 centimeters, which is in most cases thicker than a human body. We have, this could be an alternative treatment for deep-seated tumors, and we still have very good dose conformation compared with photons, so the blue curve here. So again, to wrap up on this, focused very high energy electrons, you can show that you have a reduced surface dose. See the green, the red curve here is at 0 on the surface. You have additional degrees of freedom in terms of optimization. So you can change the energy of the electron beam, and you can also change the focusing geometry. The dose is very conformal, and it reproduces the Bragg peak, basically the Bragg peak that we see with protons. And the dose is even conformal for deep-seated tumors, which is another set of simulations I'm not showing here. So this is all very promising, and this is still work that we plan to study experimentally. Focus beam have not been laser-driven focus beam in radiotherapy have not been studied yet in the lab, but that's something we plan to do. Now I'll quickly discuss one of the conventional solution for well, electron beam radiotherapy delivery. So that would be an array of LINAC around the patient that would send diverging electron beam onto the patient. So the advantages here are you have no moving parts, so that can improve the precision, and you have multiple beam lines. That means that you can, in theory, reduce the treatment time. Now, the disadvantage is that your source will be at the very beginning of the LINAC line, meaning that you have to shield the line all the way up to the patient. So you have to shield for X-rays, but you also have to transport these electron beams, meaning you need magnets and the vacuum system all along the LINAC. This might be problematic to split between different treatment rooms. And again, since there is no moving part in this case, this might be specifically designed for a fixed type of cancer shape and location. Now, someone came up with an equivalent ID for laser-driven sources, where laser would be the gray part here, and then you would have a couple of mirrors in vacuum sending to a focusing optic here, and then the target would be there, and you could potentially have a set of focusing optics if you wanted to, and then the patient would be right after the source, basically, and this arm here with the mirrors, the steering mirrors, could potentially rotate around the patient. So what that means is that you need much less shielding, because the source is produced right before, well, where it's used. It's very easy to share between different treatment rooms. You can just turn a mirror, basically. You can, by changing the laser parameters or the source parameters or the target parameters, you can change the energy charge, the energy spread, and potentially the dose rate. This also could be multimodal, in the sense that if you change the target here to a solid target, you could potentially use it with proton beams. You could have multimodal, so you could have electrons as well as X-rays at the same time. So it's quite versatile, and it might be suitable for all types of cancer. But again, this is not even a prototype. This is just an idea. Now, leaving VHE for a moment and going to flash irradiation. So what I discussed earlier was that flash is when you irradiate some tissue at a dose rate higher than tens of grays per second. And so we have very limited data available today, but what it seems to be is that it keeps the same toxicity for cancerous cells, but it diminishes the toxicity on healthy tissues. What could be happening, and again, this is state-of-the-art research. This is not really, well, this paper here is from 2020. But what could be happening is that high dose rate would lead to oxygen depletion in healthy tissues. And oxygen depletion there would mean these tissues are less sensitive to dose. So that would mean they're not as well, they're not as sensitive to dose, so the toxicity is reduced. But again, this is not fully understood at the moment. Although it is not fully understood, it's been tested on humans. This here is a 75 years old man who had a lymphoma, multi-resistant lymphoma on the knee, where they treated him with 5.6 MeV electron source, 1 microsecond pulse duration, and it seemed to have recovered very well. So this flash type of therapy is something we could study both with our side electron beam, since it has such a high charge, and even if the pulse duration is a little bit longer. And we could also study this with the forward electron beam, high energy forward electron beam, because the pulse duration is so short. So that we could look at both sides of things, given that with low energy electrons, you would only be able to reach superficial tumors, and with the higher energy, you could go deeper into the tissue. But this is all very interesting. This is all research we're planning to do. Now coming back on the other media that we can use for radiotherapy, X-rays is the most used today, even though the deposition is not conformal as we would expect it to be. So this curve here in blue is for 6 MeV photons, but again, they are still the most widely used in radiotherapy now. What you could think is, well, we could just focus those X-rays, and that would potentially lead to the same effect as for electrons. But these type of photons have a very high energy, so hence trying to focus them with classic optics, just putting a mirror and then trying to focus those X-rays, well, these photons will just go through anything. So it's quite hard to focus them. So one of our colleagues came up with the idea of using Bremsstrahlung, the Bremsstrahlung scenario, but with a focusing electron beam. So here on the left is the electron density map, if you wish, and fluence map, by the way. And on the right is it is for the photon. So what you can see is you have a focused electron beam hitting a target that's in blue here, and it will keep focusing afterwards. And then that leads to the production of an X-ray beam that is focused, and that is focused. And what's been shown is that having a focused X-ray beam can lead to a lower spread of the dose deposited, and it can allow to reach deeper seated tissues as well. So this is all very interesting. This has only been published last year, and this is still research that's going on in the group. But yeah, this is very interesting. Another thing we can do with X-rays is radioisotope production. So radioisotopes are used in several different fields in radiotherapy. They are used as treatment devices, but also as imaging devices, such as in the positron emission tomography scan, where basically you would ingest radioactive material, so a radioisotope that's glued onto some sort of sugar, the sugar will specifically fix on high metabolism part of the body, basically. And we know that tumor is a high metabolism part. So basically, you'll have these radioactive material that will specifically glue to where the tumor is. What will happen is that these radioactive material will emit some positron, and these positron will decay with an electron emitting 2 annihilation photons. Now, if you can recall these 2 annihilation photons, then you can trace back where they come from, and that will give you a map of the tumor location and shape. And this is now widely used in radiotherapy diagnostics. So about 140 isotopes are used worldwide, and about 10 of them cover 90% of the need in terms of medical imaging. And if you take the specific example of technetium-99, it covers 80% of all the need in imaging diagnostic related to radiotherapy. Now, in 2008, 2 reactors shut down for maintenance, I believe, and that resulted in 70% of the procedure cancelled or delayed. So that shows you how crucial it is to develop new ways of producing these radioisotopes. Another thing that could convince you is that this is basically the age of the reactors that are used, and what you can see is most of them are well 35 plus years old, which again tends to show that we need to try and develop new ways of producing this radioisotope. So what can laser-driven sources do in this case? Well, again, we can use electron beams and convert them through Bremsstrahlung into X-rays or gamma rays in that case, and then have them to hit a specific target. In our case, this is thorium-232, and this is because thorium-229 is involved in a chain reaction leading to actinium-225. And that actinium-225 is used in radiotherapy as in direct therapy, but also in imaging diagnostics. And this is only produced in 2 reactors in the US and in Germany. And we've shown through Monte Carlo simulation that actinium-225, so this small peak here, would be produced under our experimental conditions. And this experiment is currently going on in the lab. Okay, so we can use X-rays for what I've just shown, but we can also use X-rays to do imaging. But in this case, we won't use Bremsstrahlung just because the difference between Bremsstrahlung and betatron makes you lean to choose betatron rather than Bremsstrahlung in this case to do highly resolved imaging. So this is a typical setup for a betatron experiment where you have your laser pulse focused on the gas target. You block the remaining laser pulse, and then you have X-rays and your electron beam, your betatron X-ray and your electron beam that will go through. You have a target that you want to image, then you bend your electrons away, and you collect your X-rays onto a CCD camera. And here what you make use of is the very small source size of your X-ray beam. It's a couple of microns basically, meaning that you can achieve very high spatially resolved images. This is here the head of a fly. This here is a bee. And this is bone samples imaged at different energies. And you can see, well, on all three, well, mostly on these two images, you can see that the resolution is very high, and this has a potential in as a radiobiology diagnostics as well. Now the last application I want to discuss is related to protons. So as I discussed earlier, due to this bragg peak type of behavior, this is the most efficient, if you will, way to treat tumors. Although the main issue with this is it requires very expensive facilities, lab space, and equipment. So again, our thinking here is, can laser-driven sources have a role to play in this scenario? So for proton therapy, you need an energy of, well, at least 70 MeV. Now, the actual record using, for laser-driven proton sources is of about 100 MeV, and that's the very tail of this green curve here. So you can see that if you use one of these spectrum and irradiate a patient with it, it will spread the dose. You will have multiple bragg peaks at each energy, and that will lead to a very broad dose deposition in this case. And again, you need at least 70 MeV energy for the protons. So this is 100 MeV record is still a little bit short. Another thing you need to control is the shot-to-shot reproducibility, the repetition rate, and the divergence. As I said, the divergence today is about 10 degrees, which means that you will irradiate not only the zone where the tumor is, but also the surrounding tissue, which is, again, what we're trying to avoid. But work's been made towards this, where you have a laser pulse that's used in this setup to generate your proton beam, and then a second laser pulse is used to try and focus part of it. So now if you look at these images here, this is the 9 MeV proton beam, this is the 7.5 MeV proton beam, and you can see here a brighter spot, a darker spot, sorry, meaning that you have collimate, well, you have focused at least partially this 7.5 MeV proton beam. There's still progress to be made, but some have been made already. You could also think about using proton sources for radioisotope production, because the requirements are not as strict as for radiotherapy directly. And that's something that's been looked at in 2004, where they used 40 to 50 MeV proton beam to generate carbon-11 radioisotope, which is again used in imaging diagnostics. The problem here, well, if you call it a problem, is that the overall activity is still below the conventional accelerator level. So you would need to improve either the repetition rate or the yield per shot of activity. But still, this is progress made, and this is going in the right direction. So to conclude, I think there is room and need to improve both the radiotherapy treatment modalities and the diagnostics surrounding it. Well, room because of, as I said, X-rays are still the most used mean, but the conformity is not the best, and need because the number of cases might improve in the next years. And I think laser-driven sources could have a role to play in this field, although they need still a lot of improvement. This is a field that's evolving quickly, and it is very exciting. I'll just give a few words on the lab I'm part of, which is called SCAPA, for Scottish Centre for Applications with plasma accelerators. So we are focusing on applications, research and development. We have 3 shielded areas containing 7 accelerator beamlines. And we have 3 high-intensity lasers, and our goal is to produce high-energy proton, ion, electron benches in order potentially to drive high-brightness X-ray and gamma rays. Here I listed a few of our of the applications we're working towards. And here are my references, and thank you very much for your attention, and please let me know if you have any questions.
Yes, Neena ma'am.
Okay. Thank you, sir, for enlightening us with your knowledge. It's now time to move on question and answer session. We would be taking questions from YouTube and Zoom chat box. Now I request Dr. Vikas Katosh, Dr. Pavan Kumar, and Dr. Amish Sharma to attend the audience for question and answer session. I over to you, sir.
Namaskar, ma'am. Hello.
Yes,
Am
sir,
I
you
audible?
are
Audible, you are audible. Any questions?
Ma'am, I am from YouTube channel. There is no question, but a very nice comment. It was very informative session, very nice session, or good information. There is no question on YouTube.
Okay,
Hello.
thank you.
Okay, thank you, ma'am.
Hello, madam. There is one question from the Zoom. Hello, Antoine.
Sir, go ahead.
Which is the best method to produce the tunable monoenergetic beam of proton? Also, what type of laser is used in a journal? This question is asked by Narendra Kumar.
Sorry, can you repeat the first part of the question?
Yeah,
I'm not sure I understand.
Which is the best method to produce tunable monoenergetic beam of proton?
Oh. Monoenergetic beams of protons is something people are working on, but well, again, I'm not an expert in laser-driven proton sources, but I think this is still something people are working on, and this is not something that's been achieved consistently. It is very hard to produce, given the physics that's used to generate protons. It is very hard to generate them in a monoenergetic way. Now there are new ways of generating them which I've not discussed because they require higher intensities, and they may lead to smaller energy spread proton beams. But at the minute, it's still something that's at the heart of the research on laser-driven proton beams. And then the other question was on the material used in proton acceleration. And again, I'm not an expert, but I think this ranges from metallic to plastic type of materials, because what will most of the time happen is that so the hot electron will escape through the back surface of the solid target you're using, and the protons that will be accelerated are the ones sitting on this back surface. So it doesn't necessarily mean that the protons that will be accelerated are from inside the target. They could be from the surface, the back surface of the target, meaning that could be just water or carbon. Well, basically some dirt that came onto the surface of your target, basically. I hope I answered the question.
And my question, and I have one question. Hello, Antoine.
Yep.
I have one question. Which is best among the which is the best target normal sheath acceleration or radiation pressure acceleration? Which one is best?
Oh, that is a tricky one. I'm mostly focusing on laser wave field acceleration, so on electron
Okay.
acceleration.
Oh, yeah, yes. Okay. No problem.
So I could not comment on that. I think both of them have advantages and disadvantages, and it depends on what type of laser you have available. And yeah, this is a tricky question, I think.
Oh, yeah. Okay, thank you. Thank you for a wonderful lecture.
Dr. Antoine.
Yeah.
Dr. Antoine, could you please tell me in 1 or 2 lines the advantages of laser-driven sources over the conventional sources used in the radiation therapy?
So, I mean, if you're talking about now, like today, I think we're still quite far from using laser-driven sources in radiotherapy. We still have to improve all these sources, either as electrons, X-rays, or protons. But I think in the near future, it might be that, I mean, laser technology is developing so fast that it might be that in the near future, it is competitive to use laser-driven sources compared to conventional sources because of the versatility and the fact that they're not as expensive, potentially not as expensive as conventional sources. And
Right.
I think that's, yeah.
That is the main advantage. Yes. Thank you, sir. Thank you.
Hello, Mr. Antoine. One question from YouTube by Dr. Manoj Mangal. What type of laser used for cancer treatment?
So again, today there's no laser-driven sources that are used for treating cancers. This is all research that's being done at the minute to improve the characteristic of the sources we are driving. We're driving with lasers, but what we use at the minute is terawatt to petawatt peak power lasers. That means a couple of joules to a couple of joules to 100 joules, and a couple of femtosecond to hundreds of femtosecond laser pulses. That means, again, yeah, terawatt to 10 of petawatts. But again, this is not yet used in radiotherapy. This is to come, I think, but not tomorrow or the day after.
Okay, thank you, sir.
I think there was one hand raised. Now I can't see. If somebody wants to ask question, they can raise hands. I think no one. So question answer team, can we close?
Yes, ma'am.
Okay, over to you, Nina.
Thank you, sir. Now we will be ending question and answer session. Thank you, sir, for taking the queries. Now I would like to request Dr. Abhinav Agrawal, Dean Academics, RKGIT Pharmacy, and coordinator of this webinar series, to propose vote of thanks. I over to you, sir.
Thank you, madam. Am I audible?
Yes, sir, you are audible.
Okay. It is indeed a privilege to present a vote of thanks on this occasion. First and foremost, we must express our gratitude towards Dr. Antoine Maitrallain for accepting our invitation and sharing with us the developments in the field of radiotherapy. We thank you, sir, for quenching our intellectual thirst. We must also express our thanks towards Shri Dinesh Goel ji, Chairman, RKG Group of Institutions, Shri Akshat Goel ji, Vice Chairman, RKG Group of Institutions, and Dr. Lakshman Prasad, Group Director, Rajkumar Goel Group of Institutions, for their continuous motivation for every event at RKGIT. I extend my deepest regards toward Dr. D.R. Somsekhar and Dr. Monica Sachdeva for providing committed leadership and motivation at RKGIT and RKGIT Pharmacy respectively. I must also thank Dr. Poonam C. Kumar, Head of Department, Applied Science and Humanities, RKGIT, for an immense contribution in the organization of this event. I must also mention special thanks towards the participants of this webinar series for their constant support even during such trying times. I shall be failing in my duty if I do not acknowledge the contribution of my colleagues Professor Sanjeev Goel, Dr. Pawan Kumar, Dr. Vikas Katoch, Mr. Pankaj Sharma, Mr. Santosh Mishra, and Dr. Neena Sharma for their untiring efforts in making an event of such magnitude possible. Thank you all once again. Over to you, madam.
Thank you, sir. Feedback link for the webinar series will be shared on the last session of webinar series, that is tomorrow. And after filling the form, your certificate would be shared on your registered mail ID. We have to come to our day 2 webinar series. Thank you for joining us for today. It is indeed a pleasure to have you with us. Please turn on your video for a snapshot, everybody, please.
All the team members. Monica ma'am kahin chali gayi?
Is enough, ma'am? Shall I take?
Yeah, I don't think so anybody is coming.
One more, ma'am. Okay, ma'am, it's done.
Thank you, Dr. Antoine. It was a wonderful session and very informative.
Thank you very much for having me.
And hope we can have your session sometime physically also, online. You can visit India and give us some information on the talk in India. We would love to have you in India. Thank you so much.
Thank you.
That's all for now. Thank you.
Thank you so much.
Ma'am, you were late, I think. Monica ma'am?
Hanji?
आप late थे? You were not there for the picture?
No, I was there, I think.
ठीक है, it's fine. Otherwise, we would have taken a, again, we would have taken a shot.
I was there.
Okay then. Okay. Thank you, everyone. Thank you so much.
Thank you.
Thank you very much.
Pankaj sir, I think.
Yes, madam.
Thank you, ma'am. Pankaj sir, we can.
Thank you. Bye.
Thank you. Bye. Bye. So, Pankaj sir, 2-3 minutes we can switch it off.
Yeah, ma'am.
2-3 minutes.